Okay, I think we're ready to go here. Okay, so the mean value theorem, what this does is it connects together the concept of average rate of change with instantaneous rate of change. Basically, what it says is if you have some kind of function and it has to be continuous, differentiable, so there's no breaks, it's nice and smooth, all that good stuff. So let's say here's our nice, smooth, no discontinuities function, f of x. If you put some interval in there, say it from a to b, and you figure out what the average rate of change is between those 2 points, i.e., what is the slope of this line here? Does that make sense? That's the average rate of change. Change in the y divided by the change in the x. Okay, the slope of that little blue segment that I just put in there. The mean value theorem says that the slope of that little blue segment, somewhere in the interval, there is an instantaneous rate of change that is the same as that has the same slope as that. Okay, so as you're going along, and think, okay, I've got all these little tangent lines as I'm moving along in this curve. Eventually, at some point, maybe right about there-ish, maybe it's about right there. See how my tangent line has the same slope as that secant line that I put in there to begin with? Okay, so there is some value. We don't know where it is initially, but there is some value. In this case, it's about right there. Somewhere inside of that interval where the instantaneous rate of change matches the average rate of change. Okay? And we give this point, call its x value c. So there is a c somewhere in the interval a to b where the instantaneous rate of change matches the average rate of change over the interval. So in function notation, what that looks like then is this. There is an f prime of c. Okay, does that make sense? At c, see how we did the derivative because it's the tangent? So f prime of c should equal the average rate of change. Well, average rate of change is the change in the y over the change in the x. So f of b minus f of a, change in the y, divided by b minus a, change in the x. And so the first goal that we have with the mean value theorem is to determine if a function satisfies the mean value theorem. So does it meet all the criteria? And then if it does, we're going to go find this c. So where is it? So I give you a function, give you an interval. Tell me where the c is that makes that happen. Okay? All right. So I'm going to come over to the side here. We're just going to... maybe I'll just do it down here. Because this is important. So if f is continuous and differentiable, on the interval, that has to happen, otherwise this totally breaks down. It doesn't work. So when I ask you, determine if a function satisfies the mean value theorem, to satisfy it, it has to be continuous and differentiable on the interval given to you. Okay? So, for example, and this one we'll go ahead and use our calculators for. Take a look at it. pretty sure you don't know what it looks like. Maybe you do. I don't know. Probably not, though. So f of x equals the square root of x squared plus 1. And we're going to put this on the interval -1 to 1. So does this function satisfy the conditions necessary for the mean value theorem? And if it does, let's go find our c. So take a look on your calculator. Does it appear to be continuous and differentiable on that interval? Nope, not technically. It's the absolute value of x. Because if you were to put in negative something for x, this ultimately would make it positive. So it comes out as an absolute value instead. So what do you guys see? Is it going to work? Is it continuous? Yes. Is it differentiable? No. So it doesn't work. So this one we can't use the mean value theorem for. Okay, so can't do it. Okay. How about another one then? Let's do all right, how about that one? Now, you probably don't even need it for this one. But is 2x squared minus 5x on the interval -2 to 0, is that going to satisfy the conditions necessary for the mean value theorem? Yeah, we know what this thing looks like. It's a parabola, right? And any piece of a parabola is going to be continuous. It's going to be differentiable. It's a nice smooth curve. So it's going to work. Okay? So let's see if we can figure out where is C. Where is that point in the interval where the derivative there is going to match the average rate of change? So what do you suppose the first thing we should do is then to try and find that? Okay, find the derivative. Okay, done. Now what? Back that up just a little bit. I want to know, where is the instantaneous rate of change going to match the average rate of change? So figure out what the heck is the average rate of change then, right? And then we can actually compare that and see. All right, so our average rate of change is going to be f of 0 minus f of -2 over 0 minus -2. So we got to plug into our function here to figure out those values. F of 0 is 0. F of -2, what does that get us? 4 times 2 is 8, plus 10, so 18 it's looking like. And then that's going to be over 0 plus 2. So -18 divided by 2, -9. So I want to know, when is my derivative equal to -9? Okay, so we're going to take this and this and do what with them? Set them equal. Right. Solve it for x after you set those two equal. So 4x minus 5 equals negative 9. Let's see, so 4x equals, if we add 5 to the other side, we get negative 4, so x is going to be negative 1. Okay, so, or, more specifically, c, that number in between a and b, along the x-axis, has to be negative 1 to work. Okay, now here's the thing. Here's kind of a check for you. Look at this original graph that we drew here. C has to be some number that's inside the interval, right? Between A and B. You know you did it right if you're getting a number that ends up inside of your interval. Our interval was negative 2 to 0, right? Did we get a value between negative 2 and 0? Yeah, we did. So we can be pretty confident that this is the right answer. Okay? So if we were to draw this graph, draw the secant that connects the endpoints, and then drew a tangent at negative 1, they should be parallel. They should have the same slope, same rate of change. Okay? So this is going to be kind of the first thing you guys are going to be doing is searching for that C. This example that I gave you here, because it's the first one you've done, I made it kind of easy. You're going to have some other ones that might be a little bit more challenging, but I'm going to leave that to you because I think that's better for you guys to practice with those on your own and not eat up time right now. But this is the concept, though, okay? So you can kind of take this and run with it a little bit. That's the idea. That's the process that you're going to do. Now, because of the mean value theorem, this will allow us to determine where we have increasing and decreasing intervals. So that's going to be the next thing we're going to look at then, is how can we figure out where a function increases or decreases? Now, I think you guys already have kind of a sense of this based on what we've talked about before. So, I'm just curious if you know it already. What has to be true about the derivative over an increasing interval? Let's start with that. Slope is positive, so the derivative is positive, right? Okay. Well, that happens because of the mean value theorem. Okay. Over an interval, if we end up with a positive slope as our average rate of change, we know somewhere in there it's going to have to be increasing to get there. Okay, so that derivative, that instantaneous rate of change in the middle, is going to have to be positive too. So if f prime of x is greater than 0 on some interval ab, then f increases on that interval. And then likewise for decreasing, same kind of a thing, right? So if the derivative is negative, then it's going to decrease on that interval. Okay, so let's try that one. See if we can figure out some increasing and decreasing intervals for a function using that idea. Okay, so let's say we've got x to the third minus 4x. Now I want to know, where does this thing decrease, or increase and decrease? Okay, so, like with pretty much everything we've been doing, what's the first thing we're going to do?
Find the derivative.
Yeah, right. Okay, so the derivative, 3x squared minus 4. Okay. And now, we need to figure out, when is this positive and when is this negative, right? We've done this sort of thing before back in pre-calc. You guys remember when we did like the sign chart stuff and we figured out when is it above, when is it below, and all of that? No? Okay, well, we'll do that again and I'll show you. First thing we have to do is, if we want to know when is it positive and when is it negative, we got to figure out where it's 0, because that's where it changes from being positive to negative or vice versa, right? So take this thing, set it equal to 0 to begin with. Kind of like we're finding a critical point again. But those critical points are going to determine where the increasing and decreasing starts and stops. So that's where we want to start here. So 3x squared equals 4. X squared equals 4/3. So x is going to be plus or minus the square root of 4/3. Or I guess plus or minus 2 over the square root of 3 if you want to get technical there. Okay. And so there are 2 points here. There are 2 critical points where the increasing and decreasing intervals are going to change. Okay? And so those are the 2 places where we're going to set up our sign chart. So remember, our sign charts kind of looked like this. We did a number line. And then on that number line, we plotted each one of the places where it's 0. So we've got negative 2 over the square root of 3. That's where it's 0. And then we've also got positive 2 over the square root of 3. And we broke that into kind of different portions of the graph then. And then we tested in between them, plugging in numbers to see does it come out positive or negative when we do that. Okay? So there are going to be some numbers that are easier than others. Okay? Negative 2 over the square root of 3. Square root of 3 is like 1.8 something. So 2 divided by that is really close to 1. So if you want a number that's definitely smaller than that, just pick some large negative number. Okay? So over here, all right, if I take some very large negative number, plug it in, the result of this is going to come out positive or negative? Positive. Okay? So this is a positive interval over here. Okay? What's a nice number between negative 2 over square root 3 and positive 2 over square root 3? Yeah, right. So plug in a 0. Positive or negative? Negative. And then if you put in a very large number, which is definitely bigger than 2 over square root 3, positive or negative? Positive. Okay. Every interval where you see a plus is where the original function increases, and everywhere you see a minus is where the original function decreases, right? So increasing, we can use interval notation for this. So our increasing interval would be from negative infinity to negative 2 over root 3. And then also 2 over root 3 to positive infinity. And you can use your little union in between those when you're doing the increasing and decreasing stuff. That's fine. And then our decreasing interval will be what's in between there then. So from negative 2 over square root 3 to positive 2 over square root 3. And that's it. Okay. So again, you're going to have some questions in your homework that are a little bit more challenging than this, but that's the concept, though. Okay, that's the idea. That's the process you need to go through, is to take the derivative, set it equal to 0, figure out where those places are, and then test around that, and that'll tell you where it's going to be positive or negative. So where it will be, the original function should be increasing or decreasing, and you got it.
Will you ever use brackets for those intervals?
No, it's a good question. We don't use brackets with increasing and decreasing intervals because technically the points where they meet are maxes or mins, and it's not increasing or decreasing at those places, so it's just all parentheses. Yep. Okay. Very last thing we got to do. We got a little bit of time. I think we're going to make it. Calculating. If you stop laughing, we might have time.
You continue it.
The very last thing that I want to look at with you guys here is antiderivatives. Oh, sorry. You can't see that. All right. So, there is one consequence of the mean value theorem that says functions where f prime equals 0 are constant. So what that means then is if you are taking derivatives of several functions that only differ by a constant, their derivative should be the same. And this is something that we've kind of looked at before. Like if I had, let's say f of x was 3x squared plus 5, and g of x was 3x squared plus 8. Those two would have the same derivative, right? Both of these things, f prime of x equals 6x, g prime of x equals 6x. So, we can do antiderivatives. And basically an antiderivative is going backwards. So if I start with this, going back to this. Okay? Now, do you see a little problem with that, though? If I said find the antiderivative of 6x, there's more than one answer, right? There's lots of different functions you could have had to get a derivative of 6x. Okay? So the way that we would write this then is the antiderivative of 6x is 3x squared plus c. And what do you suppose that plus c stands for? Right, it just means constant. Okay? And I just have to leave it like that because I don't know what the constant was. It could have been anything. But I do know this much. First term has to be 3x squared, right? Can't get away from that. But then it's going to be plus something. Okay? So the way that we write antiderivatives is we always have to put a plus c on the end of it because there could have been some constant back there that we don't know what it was because we lose that when we do a derivative. Okay? So you have to kind of think backwards a little bit, okay, when you're doing an antiderivative as to, you know, like this 6x term, okay, instead of bumping a power down, when you're doing an antiderivative, it goes up. And then think about what would the constant in front have to be to make that work. Okay? So we'll do a few more of these. And each one of these, I want to see if we can come up with what the antiderivative would be. So work it backwards. Okay, so let's try this one. 4x to the third plus 2x. Antiderivative, not derivative. Okay? An antiderivative is just doing the opposite of a derivative. We'll talk more later about like what their applications are and how we actually use them to do stuff. But for now, I just want to kind of expose you to it. So the antiderivative of this one, it would have to be x to the fourth. And what would be the coefficient in front? Nothing. The way that you do that is think about, I want to take this term. If I did its derivative, I should get this, right? So x to the fourth, I would have brought that 4 down in front, right? Well, the 4 is already there right here, so I got nothing there anymore. Okay? So it's just x to the fourth. What's going to be true of the next term then? Just x squared, right? And then what do I always have to put on the end? Plus c. Okay? So this would be the antiderivative of that particular function. Okay. It's, well, for now, there is no notation for it. Just write it out. There is a notation for it, but I don't want to let that cat out of the bag just yet. We'll talk more about that later. All right, let's do one more. Well, you could say it that way if you wanted to. You can say, here's the derivative. Like I could say, here's f prime of x, so tell me f of x. I guess that would be a way of writing it. But I don't have to do it that way. I could just call it f of x to start with, in which case, like I said, there's not really a notation for it just yet. But, okay, anyway, this next one. What's going to be the power on my first term? It's going to be up to 3. So what's the coefficient going to be this time then? What is it? 7/3. You guys all catch that? Think about doing the derivative. You'd bring the 3 down, right? Would have to cancel that 3 and make 7. So 7/3 works. What about the next term? It's going to be an x squared, right? So what's the coefficient for that one? I think somebody just said it. 5/2, yeah. See a little pattern happening here? Yeah? Yeah, good. What about the -1? Negative x, good. And then plus c. Okay. All right, I think that's enough for you guys to chew on, where you guys can stay at home tomorrow and see what you can do with this stuff.